All right, let's jump right into this explainer and completely demystify vectors. We're going to strip away all that academic intimidation and look at them for what they truly are. They are literally the fundamental physical tools that bridge our messy, discrete, real-world reality with the ultra-clean, continuous mathematical optimization of machine learning. Seriously, you can think of vectors as the absolute blueprint for exactly how artificial intelligence understands our world. So, to understand why vectors even exist in the first place, we actually have to look back at a huge representation crisis that physicists faced in the 19th century. You see, they could easily measure a scalar quantity, right? Something like temperature. A scalar is just a single number. A thermometer only tells you how hot something is. But what about things like wind, physical forces, or velocity? Those require a lot more information. A vector is kind of like a compass. It brilliantly captures both your magnitude and your direction. It serves as the essential mathematical language for absolutely anything that has more than one degree of freedom.
Let's build up some intuition here. Imagine you're describing a house to a real estate agent. You wouldn't just say, hey, it's a 3. That doesn't mean anything. You'd list multiple features, right? 3 bedrooms, 1,500 square feet, $350,000, 20 years old. By mapping these specific features into an ordered list, we are instantly hardwiring those abstract numbers directly to the physical front door and the actual square footage in your brain. And guess what? You have just created a vector. Now here is the absolutely crucial point. The position of a number in this list is just as important as the number itself. Think about it. If you just swap the first and the last numbers, you suddenly get 20, 1,500, 350,000, and 3. You've just described a 20-bedroom mansion that is exactly 3 years old, all for the exact same price. No way, right? That is a completely different house. And this is exactly why a vector isn't just a random list of numbers. It is strictly defined as an ordered list.
Okay, zooming out a bit, almost like an architectural blueprint, let's see how this concept actually scales. In a 1D space, your address is just a single number on a straight line. Easy enough. Zoom out to a 2D grid, and suddenly your address is 2 numbers, like a street and an avenue. Zoom out one more time into the 3D space that we intuitively navigate every single day, and your address is 3 numbers, X, Y, and Z. But here's the kicker. In machine learning, we are facing the exact same problem. We're just doing it in thousands of dimensions instead of 3. Before we jump into those thousands of dimensions, though, let's quickly look at the basic math. When we combine 2 physical forces, say 2 people pulling a heavy rope in completely different directions, we use vector addition. By placing the tail of one vector right at the tip of the other, we literally draw a physical parallelogram of force to find the result. And then we have scalar multiplication. This is when you take a vector and multiply it by a single number, or a scalar. Doing this merely stretches, compresses, or flips the vector without ever changing its underlying geometric track. For example, if you multiply it by a negative number, the arrow just flips 180 degrees. If you multiply it by 2, it just stretches out twice as far. Simple as that. Now, let's be honest. Human intuition completely taps out past 3 dimensions. We just aren't built for it. So to wrap our heads around a 768-dimensional space in an AI model like BERT, we have to completely shift our mental model. You literally cannot physically draw this. Instead, imagine a vast, glowing semantic nebula filled with clusters and distances. In this dark, incredibly high-dimensional room, every single word in the human dictionary is a tiny, glowing coordinate. And what's super fascinating about this space is how words with similar meanings, like happy and joyful, naturally drift toward each other. They actually bond, creating this glowing semantic cluster. On the flip side, words with opposite meanings sit on completely opposite sides of the room. This gives the machine a literal mathematical geometry of meaning. So when you add a vector in this space, you're literally taking a step through this high-dimensional room of concepts. This crazy geometry is exactly how a modern transformer model works under the hood. Every single word token gets an embedding vector, which we'll call E. But it also desperately needs a positional encoding vector, P, to know exactly where it sits in a given sentence. The model simply adds them together, stroke by stroke, X equals E plus P. Using nothing but simple vector addition, it brilliantly combines a word's deep meaning with its exact physical location. But here is where the math gets incredibly unforgiving. It demands absolute perfection. What do you think happens if you try to add a 3-dimensional vector to a 2-dimensional one? Well, the operation is completely undefined. You literally cannot add a 3D point to a 2D point. If you try this in a framework like PyTorch, it immediately throws a hard dimension mismatch error. Ask any developer, this is the ultimate gateway bug to countless frustrating hours of debugging for machine learning engineers. So the absolutely crucial takeaway for engineers here is that the shape of a vector strictly dictates how computer memory is allocated and exactly how matrix multiplications are scheduled on the GPU. The difference between a vertical column vector and a horizontal row vector, it might seem like just a quirky notation thing, but it's actually a hard physical engineering requirement. Confusing a 1D vector with a 2D matrix that just happens to have one column is the root cause of catastrophic silent broadcasting bugs. And this strict architecture, it scales across the entire AI ecosystem, from the very first embedding layer that maps discrete tokens into dense vectors, right through to the transformer attention mechanism, computing queries and keys, all the way to the final output logics of a classifier head. Vectors are, without a doubt, the absolute lifeblood of all neural networks. Without them, we literally could never process images, understand sentences, or crunch massive multi-feature datasets. Now, if we strip away all the abstract math and look directly inside the machine's actual hardware, a computer doesn't see a compass arrow. Not at all. It sees a vector merely as a contiguous block of glowing RAM cells. To access a specific element, the computer takes the base memory address and then it simply adds the index multiplied by the stride, which is usually 4 bytes for a float 32 number. This incredibly elegant math allows the computer to find any coordinate in lightning-fast 01 time.
Because of this specific memory layout, GPUs are absolutely essential to the whole process. If you try to iterate over a vector's elements using a standard Python loop, it is catastrophically slow. Instead, hundreds of CUDA cores on a GPU will add pairs of elements simultaneously. And because of this massive, incredible parallelization, memory bandwidth, the sheer speed at which we can read those floating point numbers out of VRAM, actually becomes the true bottleneck, not the compute power.
Just to put the sheer scale of this memory constraint into perspective, for a modern large language model that has a dimension of 12,288 and a context length of 4,096, just the input sequence vectors alone will completely consume 96 million bytes of VRAM. That is nearly 100 megabytes of memory just to hold your prompt. This shows exactly how a vector's dimension directly and relentlessly dictates hardware consumption. Pushing right out to the very edge of modern research, we encounter something truly wild called superposition. It's this incredible phenomenon where an AI actually manages to pack thousands of concepts into a limited number of dimensions. How? Well, it does this by explicitly trading off perfect mathematical alignment. By allowing vectors to be slightly non-orthogonal, basically accepting a little bit of mathematical interference, a single dimension can secretly encode multiple, completely unrelated concepts, drastically increasing the model's total capacity. So let's lock in our permanent mental model here. A vector is essentially a super address. It's a strictly ordered list that acts as the ultimate, indispensable bridge between our messy, discrete physical world and the perfectly clean, continuous mathematical optimization of AI. Truly, it is the fundamental currency of all deep learning representations. Every single concept, every word token, every gradient, it's all just a vector. Which brings us to the very edge of the frontier, right into what we don't yet know. As we map basically all of human knowledge into these breathtaking, continuous, high-dimensional spaces, the AI models can actually pack concepts in between other concepts. And honestly, it leaves us with one incredibly provocative thought. What undiscovered concepts are currently hiding right now in the dark, non-orthogonal spaces between our words?